So distance is the sum of all movement from a person or object regardless of the direction that it's going in. Distance is usually measured in meters or centimeters, and the equation is shown as distance equals speed times time. Distance is a scalar quantity because it has no regard for the direction, therefore it's only a scalar measurement. An example of distance as shown is the route for the London Marathon, which is 26.2 miles. And that will be how far the person moves from when they start to when they finish, how far they've gone. And then for an object, a javelin throw, the distance would be the actual arch of the throw and how long that is. So if they throw it 50 meters, the arch and trajectory of the throw will be probably push it close to 60 meters in distance. Moving on to displacement. Displacement is the distance of a straight path that an object has moved from start to finish with reference to direction. And this regard to direction makes displacement a vector quantity. Keeping with the London Marathon, the distance of the entire event is 26.2 miles, but the actual displacement for a straight line from start to finish is only 10.2 miles, as shown by the black line, which would be the displacement value. And then for an object, the football, if it's shot from the 18-yard box, it is there, then the displacement from where the ball is being struck and the goal is 18 yards, and it won't take into account the flight path and add any of that distance. It would just be 18 yards in the positive direction, and that's the same with the marathon. It will be in the positive direction or north or whichever reference to direction. So moving on to speed. Speed is the amount of time taken for an object to move a certain distance, therefore referencing the equation, which is speed equals distance over time. It's usually measured using meters per second or kilometers per hour. Speed is a scalar quantity because it has no regard to direction and therefore making it a scalar. For example, an athlete doing a 50-meter swimming race, which takes the athlete 15 seconds, using the equation of speed equals distance over time, the athlete would average a speed of 3.3 meters per second. And then for the equipment, the cricket ball, as shown, the distance between the wickets is 20 meters, divided by the time that it takes the ball to travel 1 second, which is 1 second, sorry, would therefore mean the speed is 20 meters per second. Moving on to distance time graphs. With this distance time graph as shown, the distance is on the y-axis and the time is on the x-axis. And this distance time graph is of someone running. At the start of the small red line, it's shown that the athlete started running at a constant pace, and then as they move into the yellow, they continue with a constant speed, but it's a bit slower because the gradient is less steep on that one than is on the red. So the runner's gone from increasing their speed a lot with the red and then slowly increasing their speed with the yellow until at the green they're then at a constant speed. And then once they get to the blue line, it's a decrease in speed very rapidly, and then the small orange line at the bottom would mean that they're stationary as they're covering no distance in that time. Moving on to velocity. Velocity is the rate and direction that an object moves. It's a vector quantity because it relates to the direction as shown in the definition. The equation for velocity is shown as velocity equals displacement over time, and it's measured in meters per second. just like speed. However, because it's displacement, you need to reference the direction, which could be positive direction, north, or whichever one. An example would be the velocity of a cyclist going, say, 10 meters per second as they cycle through, or in whichever direction that would be. So it could be in the north direction. And then for the hockey player, the hockey pass, the velocity would increase as the ball is striked, and then the ball would move at, say, 20 meters per second, but in the positive direction towards another player. And then moving on to velocity time graphs. In this graph, velocity, as shown in meters per second, is on the y-axis, and time, just in seconds, is on the x-axis. The first pink line, as shown, is acceleration, as the velocity is increasing proportionate to the time, and they're increasing, making that line go upwards, and which means acceleration. And then the flat blue line shows constant velocity or constant speed, as the velocity in meters per second doesn't increase at any point, but the time continues to go from 2 seconds there. And then the black line is a very sharp increase and acceleration in velocity as it goes from 3 meters per second to 6 meters per second, but it does that in 1 second, which is a very quick increase in velocity. And then the negative gradient, the downward green, shows deceleration as the velocity is decreasing from 6 meters per second down to 0, and it does that in 4 seconds. If the line would then go below the x-axis, it would mean that the person is then traveling in the opposite direction, which would be maybe the negative direction. But this graph shows only in the positive direction, but it can go into different directions. And then this is my bibliography.